Swayam Prabha. Digital India. Educated India.
Welcome back. In the last class we stopped the lecture by looking at the questions. So, there were 3 questions that we had to solve, and we start this lecture by going to solve these questions. So, the first question, again just going back, is determine the acceleration due to gravity of a planet where small amplitude waves travel across a 2-meter deep pond with speed of 4 meters per second. So, so the speed of the wave is given, right, c is given, and we have also been given the depth, alright. So, the way it is solved is, the first question, we know v or c is equal to under root g y, alright. So, v square can be written as g into y, squaring both sides. Therefore, if we want to find out g, it will be v square by y, v or c. So, v was given as 4 meters per second and y was given as 2. So, this gives us an acceleration of 8 meters per second squared. Of course, the density, there are many other things that the density depends upon, but if we say the acceleration due to gravity is less than 10, it should be less dense than the earth. I mean, very crude approximation, this is not a very clear answer, but more importantly finding out this acceleration due to gravity was important. Second question, it has told us to ask, it has asked us to find out the flow regime, alright. So, we know that q is given by area into velocity, okay. Therefore, we have been given the discharge, right, we have been given the area. So, area is 3 into 2 and the q was given as 10. If you go back and look at the problem, it says that the rectangular 3 meter wide, so this was the width, carries 10 meter cube. So, this was discharge at the depth of 2 meter, this was d. Now, if this is asking if the flow is subcritical, supercritical. So, Froude number is given by v under root g y. So, v we have already found out using the discharge, it was 1.66 from here, g is 9.8 and depth is given as 2 in the question itself. So, this comes out to be 0.376, which means Froude number is less than 1 and therefore, the flow is subcritical, very simple to solve. Now, and the second part was we have to find out critical depth, alright, for the same flow conditions. So, if the same flow conditions is there, v is not going to change, the only thing that we can change is y, okay. And for the critical depth, Froude number has changed from 0.376 to 1, therefore, y will change. So, if we use this equation, v by under root g y is equal to 1, therefore, substituting v will remain same 1.66, g is 9.8 and y we have to find out. Using this equation we can find out y is 0.281 meters. So, it has to be less shallow, alright. Earlier the depth was 2 meter, here we have to make it 0.28 meters. So, before starting the third question, we should now just relook what the third question is. It says that the trout jumps producing waves on surface of 0.8 meter deep mountain stream. What is the minimum velocity of current if the waves do not travel upstream? Alright. So, just going back, okay. So, what I am going to do, so basically there is a velocity v of a stream and there is speed c of wave. So, we have to find v such that it is greater than c. All right. So, first we find out the speed of the wave, which is dependent only on depth. Depth is given 0.8 meter. So, this comes out to be 2.8 meters per second. All right. So, if the stream speed is greater than 2.8 meters per second, this means the trout won't travel upstream. Okay. So, that is the answer. All right. So, now starting with a brand new subtopic here, what is the total energy in open channel flow? So, coming back from classification of open channel flow to the development of surface solitary waves due to a disturbance, because free surface can distort, we are going to see what the energy in open channel flow is. All right. Here we have assumed, I am going to go into more detail, but first try to explain you a figure. So, this is the horizontal datum, this is any level, okay, and our channel is like this, and the bed slope. So, all the surfaces in the world might not be horizontal, it could be at a very small angle, okay, to the horizontal, and let us say that small slope of the channel is, let us say, S naught, will be a very small value, but anyways to be able to consider there is a slope S naught. All right. If at cross section 1 the depth of the flow is y1 and the velocity here is v1, and at section 2 the depth is y2 and the velocity is v2, we have indicated what the because of speed v1, this is the energy line and other stuff, v1 square by 2g, v1 v2 square by 2g, and this is the total head, and if going from one point to the other point the head loss is HL. We will come to these terms again, and this is something SF that we will come back to again what this slope SF is. SF is generally the slope of the energy that is lost, but that we are going to come very soon now. All right. So, this is actually a representative open channel geometry. So, going back again, I was saying that all the channel will have a small slope. So, the slope of the channel bottom S naught can be actually found out how? If the height of this particular point is Z2 and this is Z1, then S naught will be Z1 minus Z2, and if this is the length of the channel that we have considered, it will be Z1 minus Z2 by L. And we assume that the slope of this channel S naught is assumed constant over this entire length, and this actually is very small S naught. As I said, the fluid depths at two cross sections are y1 and y2. The fluid velocities are v1 and v2 at two cross sections. Under the assumption of uniform velocity profile across any cross section, we assume that the velocity profile is uniform and not like the boundary layer that we have seen in our previous week's lectures. Okay. So, under the assumption of uniform velocity profile across any section, one dimensional energy equation for the flow is, we say that P1 by gamma plus V1 square by 2g plus Z1, this is energy at section 1. Okay. At section 1 is equal to P2 by gamma plus V2 square by 2g plus Z2 plus head loss HL. So, if we assume if there is a head loss HL, then this is, if we account for energy loss, then our energy should be conserved, right, if we know how much energy has been lost and we add it to the system. So, this is energy at section 2, all right. Actually, this is another way of writing. We can also write the slope of energy line. So, we had said that if HL is the head loss or energy loss from going from point 1 to point 2, and if we divide it by length L, we can also write it in terms of slope. So, if we say SF is the slope of then we say it as HL by L, where L is the length of the channel in the consideration, and this is called friction slope. Okay. So, under the assumption of hydrostatic pressure at any cross section, if we assume hydrostatic pressure, P1 by gamma can be written as Y1, all right, under hydrostatic, and P2 by gamma is written as Y2. So, under this one and this one, our energy equation from this changes to so P1 by gamma, this is P1 by gamma, this is P2 by gamma. V1 was on this side, on the left hand side, while going it becomes negative on the right hand side, and same about S naught, because okay, I think I should go back here and try to do this on this slide, it would be much more easier. So, P1 by gamma was Y1, this is Y2, all right. So, P1 by gamma, see I am writing the left hand side, it is becoming Y1, all right, and we bring this one on this side, the P2 by gamma on the other side becomes Y1 minus Y2. Let us concentrate, we also write V2 square minus V1 square. So, V1 we have brought on this side plus Z2 minus Z1 plus HL. Okay. So, I am writing Y1 minus Y2 is equal to V2 square minus V1 square by 2G, Z2 minus 1. So, you remember what this Z1 minus Z2 was S naught. So, it becomes minus of S naught L, small l, and HL is SF into L. So, it becomes Y1 minus Y2 is equal to V2 square minus V1 square by 2G plus L SF minus S naught, same as given in the next slide. Okay. This is the equation, simplified equation that we get, all right, and this we call as equation number 7, or in other word we can say, so at energy at 1, energy grade line at 1 is E1, which is Y1 plus V1 square by 2G, and on the right hand side E2. So, if we say E1 is equal to Y1 plus V1 square by 2G, and E2 is Y2 plus V2 square by 2G, then we get E1 is equal to E2 plus SF minus F naught S naught into L. Equation at where E is specific energy. What is this E? We call E as specific energy, which is given by Y plus V square by 2G at any point. You know, at any point, but the specific energy is given by Y plus V square by 2G. So, this is a new concept called specific energy, to which you have been introduced now. It is the sum of the depth. So, the depth and the kinetic energy head. All right. And this is equation number 9 that we are talking about. So, going to more detail into specific energy, if we start from equation number 8, what was equation number 8? It is E1 is equal to E2 plus SF minus S naught into L. All right. If head losses are negligible, then SF is equal to 0, that is true. Then SF minus F naught in that will become minus S naught into L or Z2 minus Z1, correct. Then equation 8 can be written as E1 plus Z1 is equal to E2 plus Z2. How? I will just show you, it is better to show. Okay. So, equation number 8, if SF is 0, okay, and S naught is given as Z2 minus Z1 minus Z2 by L. Okay. So, E1 is equal to E2 plus minus S naught into L, and S naught is given as Z1 minus Z2 by L, correct. So, S naught L. So, E1 is equal to E2 plus minus of Z1 minus Z2. Okay. So, E1 is equal to E2 minus Z1 plus Z2, and if you bring Z1 on this side, it becomes E1 plus Z1 is equal to E2 plus Z2. All right. So, this is the result that we have got, which indicates that the sum of specific energy and the elevation of the channel bottom remains constant if the head losses are negligible, all right, in a frictionless case. Now, for the specific energy, we consider a rectangular channel with a constant width of B, something like this, all right, and having height y. So, small q is going to be capital Q by B, okay, discharge per unit width. Q is given by velocity into y into B. So, small q is going to be V is the velocity into the depth. Now, using this equation 9, what was equation 9? So, equation 9 was E is equal to y plus V square by 2g. So, equation 9 was E is equal to y plus V square by 2g, and if we use this thing in equation number 9, y will remain y, and instead of V we write small q by y. So, we can write q square by 2g y square, all right. So, in terms of y and small q, we have written E is equal to y plus q square plus 2g y square. If you see, this is a cubic equation in y. Anyways, we will come to it, all right, and this is written as equation number 10. So, for this particular case, for equation number 10, if we plot equation number 10, this is the type of curve that we get, okay, where E, a specific energy, has been plotted against y, all right, for specific small q's. So, we have fixed small q's and tried to plot E as a function of y, and this is what we get. We are going to go on it one by one. So, for a given q and E, so if we choose a small q and E, equation 10 is a cubic equation in y. So, for that there are going to be 3 solutions, all right. y super, y sup, y sub and y negative. So, if you take on one curve, there will be 3 y's, this will be 1, this will be 2 and this will be 3, all right. So, actually y negative, because this is negative y, this will have no physical meaning, y negative will have no physical meaning. Y sup and y sub are termed as alternate depth. So, this one and this one are actually called alternate depths, okay. Because it is cubic equation, we get 3, 1 is not possible and the 2 are called the alternate depths. Do not worry about sup and sub and negative for now. Now, my question to you is, I have some question. What does this line represent? Y is equal to E. Secondly, what does y is equal to 0 represent? Where is y is equal to 0? Y remains 0 all the time. So, this is the line, all right, on E axis, and we also have to prove that y sub is greater than y sup. Of course, we can see this, but we have to show, all right. So, the answer is y is equal to E corresponds to a very deep channel flowing very slowly. Why? Because E is written as y plus v square by 2g, and this will go to y as y goes to infinity, because in a deep channel y is very deep, all right. Secondly, y is equal to 0 corresponds to a very high speed flow in a shallow channel, because if you see E is given as y plus v square by 2g, because in a shallow channel this term will turn out to be v square by 2g as y goes to 0, all right. And the third is y sub is greater than y supercritical, all right. See the figure, because this implies that velocity of supercritical is greater than velocity of subcritical, as q is equal to v y is constant, all right. So, q is given as v into y, all right. So, from the figure we can see that y sub, if y sub is greater than y sup, then v sub has to be less than, all right, because q is equal to v y is constant, all right. Now, the class question is, in specific energy diagram determine y c in terms of q, also determine E min in terms of y c, and determine v c, determine Froude number, okay. So, let us go and see what E min and those things on the diagram is. So, this is the diagram, this is energy minimum, right, all right. This is y critical. So, this should correspond to critical flow depth, this is y is equal to E and things like that, okay. So, we are going to solve this question. Look at the question once again. So, determine y c in terms of small q, determine E min in terms of y c, determine v c, okay, determine Froude number at critical depth. So, everything is about critical depth, all right. So, we start with the equation that we already know. So, we know this equation, E is equal to y plus q square divided by 2 g y square, correct. This is equation number 1. Now if we want to obtain E minimum, we have to set dE by dy is equal to 0, and if we set dE by dy is equal to 0, then it becomes 1 minus q square minus 2g y cube, something like that, right? Yes, or 1 minus q square by g y cube is equal to 0. All right, I will take down this. So, dE by dy is 1 minus q square by g y cube is equal to 0. So, to solve this, and this will give the corresponding y that is going to come from this equation is going to give us y critical, correct. So, we can write q square is equal to g y cube. So, that means y cube is y cube can be written as q square by g, that means y is given as q square by g to the power 1 by 3, and because it is critical we write at critical. So, that is yc. All right. So, that is the first thing that we obtain, yc in terms of q. This is equation 2. Subscript c here denotes conditions at E minimum. At E minimum we say critical condition. Now, if we substitute yc into equation number 2, so if we substitute yc in equation number 2, yc in equation number 1, so E will be y plus q square by 2g, and now yc we have got q to the power 2 by 3 into g to the power 1 by 3. No, we can actually use the value of q square, sorry, erase alling. So, we can use E is equal to yc plus q square can be written as g yc whole cube divided by 2 g yc whole square. So, g and g will get cancelled, all right, yc cube will get cancelled with square. So, E will be yc plus yc by 2, that is 3 yc by 2, and let us see our solution at the back, 3 yc by 2, all right. So, E min is going to be 3 yc by 2, and since q is equal to Vy is constant, we can obtain Vc, right. So, this is going to be q, we already know in terms of yc and g. So, we are going to get at critical under root g yc, which we already know at Froude number is equal to 1, Fr is equal to, now Froude number is Vc by under root g yc, so that is going to be 1, but anyways we will calculate. So, Froude number is coming to be 1. So, actually we have only looking at the curve without assuming that it was already a critical flow, we have derived this. So, Froude number at this particular point came out to be 1. So, this is the point where the flow regimes are separated. I will just go back to this. Okay. So, we have calculated this just looking at by plotting the figure, that is why this was subcritical and this was supercritical. Okay. There will be a similar curve like this here as well. Okay. There will be a negative here, there will be a sub here, sub and E min. So, for each q this is a different case. All right, So, we will solve a small question. The question is, a rectangular channel has a width of 2 meter and carries a discharge of 6 meters cube per second at a depth of 0.20 meter. Calculate the critical depth and specific energy at critical depth. So, we have already seen that at so, if we write in terms of capital Q, we can write actually AC, in terms of area. These, if this is the B, this is the channel width, all right, and AC is, AC simply is the area. So, we write B by C, all right. So, not B by C, a whole cube by B. All right. Hence, Q square by G is equal to YC whole cube B cube by small b. Therefore, we can write Q square by B square by G is equal to YC whole cube. Okay. I mean, we already know YC is Q square by G to the power 1 by 3. So, Q we already know from this question, capital Q we know. So, 6 divided by 2 per unit width is 3 meter cube per meter per second, all right. So, simply YC we can get YC is Q square is 3 square divided by 9.8 to the power 1 by 3, 972 meter, and velocity is all right. So, 6 divided by 2 into 0.972, and that comes out to be 3.087 meter, all right. Or specific energy is 3 by 2, you can you can either do 3 by 2 YC, or just you can VC, YC. I will just erase everything and now simply try to do it with the knowledge that you have. So, in the derivation we know that capital Q by B, right. So, 6 by 2 is 3 meter cube per meter per second, right, all right. And YC by our formula is Q square by G to the power 1 by 3. That is what it came, correct. So, substitute in the value. So, 3 square by 9.8, right, to the power 1 by 3, and this gives 0.972 meter, all right. VC is small q by YC, because that was the equation that we were using. VC is small q by YC. So, 3 divided by 0.972 is equal to 3.087 meters per second. EC is equal to so everything VC is known, YC is known, and this is small q. So, this is how you will solve this question. So, just going at critical depth, it is a general approach. Okay. So, I have included these solutions so that it is easy for you to when you get the slides you can actually see, all right. So, this is a different method of solution. So, we have another question, but we will like to stop at this point right now, and start our next class by solving this question. Thank you so much.